The next topic that we will go through is heteroscedasticity versus homoscedasticity. So, what homoscedasticity means? If we have a model with one independent variable x, and we also have its residuals. If we have distribution of our data equally distributed along the sample, then we have stable variance, we have stable data set. What it means actually that variance of some residuals is equal to variance of some other residuals in the data set. So it is never really equal, but it is approximately equal. So variation in this sector is similar to the variation in this sector and also to the variation in the third sector. So we can say that we have approximately one variance, or our variance is constant. Then we have the case of homoscedasticity. So then our data are homoscedastic, which is actually something that we wish to have. You probably remember the same graph, the similar graph from before. So we have here one dependent variable, savings, and one independent variable, income. So what we have in homoscedastic model is that variance for the value of x10 is equal, variance of residuals is equal to the variance of residuals when x is 20 or when x is 30. So it is not only that first assumption that we talked about is satisfied, that on average residuals have the value of 0, but also that their variance is constant across the data set. The problem is if we have heteroscedasticity. You can see it on the picture when you don't have the same variance. So variance in the first part of the data set is much bigger in comparison with the data set with the variation in data set later on. This is very big problem in the data, and if we have this problem, we need to solve it. Anyway, this is why we need to draw a plot or scatter diagram of our data, independent and dependent variable on the vertical axis, so that we can see at first visually if we have such a problem. So in the case of heteroscedasticity, we don't have constant variance, and this is the problem. When it can show up in real life, for example, age versus earnings. In the younger age, majority of people are earning similar amount of wages because they are young, they are still apprentices, and they don't earn enough money. But during the age, some of them will have a much more wages, and then we have the spread. So variance is much bigger later on in our data when it comes with age. In the case of video games, for example, at the beginning, everyone is bad at the game, and really fast, the game will be over. Everyone will fail. Everyone will lose his lives. But during the time, some players will getting better and better, and they will stay in the game longer and longer. But the others will still be bad in the game. So we again have the spread of data later on. Or for example, when it comes to size of stores, sales of groceries. If stores are small, probably individual purchase of groceries will be smaller. But if stores are bigger, with a bigger offer, then bigger supply, then probably some individual purchases of groceries will be bigger. So again, we will have more spread in our data and bigger variance in our data if stores are bigger. Also, if it comes with the income and consumption, if someone has small income, if people have smaller income, so consumption will be smaller. But if income is bigger and bigger, then consumption in some cases will be much larger, while in some cases people will still save the money and consumption will be small. Again, the spread of data or variance will be bigger with a bigger income. In our case, with the test score and the student-teacher ratio, this is the distribution of our data, and we can see that more or less our data are stable, but anyway, variance is bigger with the higher student-teacher ratio. We can say that we have satisfied the first assumption, the distribution of residuals is 0, but variance at the beginning, variance in student test scores for smaller classes is smaller in comparison with bigger classes where variation of the test scores is bigger. These are some classical cases of homoscedasticity and heteroscedasticity. So first case is plausible. This is what we would like to have in our data, where variance is more or less constant. Then we have first case of heteroscedasticity, where variance is at first small and then bigger and bigger, or the opposite, first is bigger and bigger and then smaller and smaller. Also, it could happen this way, that we have first big variance, then small, and afterwards again bigger variance. Again, we need to have scatter plot at the beginning of our data analysis, that we know if we potentially have the problem with heteroscedasticity. Implications of homoscedasticity. If we have good data, what it means actually. So, estimators of beta 0 and beta 1 remaining unbiased and consistent. So, beta 0 hat and beta 1 hat will be unbiased and consistent. It will not happen if we have heteroscedasticity. Sampling distribution is still normal. Standard errors of beta 0 hat and beta 1 hat are different. They are simplified. We can calculate them through simple formulas. So this is the key step. If you have homoscedasticity, you can use simple formula for calculating standard errors. If you have heteroscedasticity, you need to calculate a more complex formula, which is heteroscedasticity robust standard error. This is the option that we have in our software. So we can turn on that option every time when we are suspecting that we have heteroscedasticity. Also, if we have good data, homoscedastic, beta 0 hat and beta 1 hat are efficient and best. So we will get blue model, best linear unbiased estimators. In reality, unfortunately, homoscedasticity is rare, and we are using formulas with White's correction. So this is that formula that I was talking about with the heteroscedasticity robust error. It is designed on the basis of the White's correction, and in most cases we will use that option in order to protect ourselves from heteroscedasticity. So, in the case of, just to repeat, in the case of homoscedasticity, we are expecting that we have one variance, one constant variance in our data set. In the case of heteroscedasticity, you see this small letter I here, it means that we have many variances, that we have more than one variance because our data are not stable. Variation of our data across data set are not constant. And this is why we have more than one variance. So, if third assumption holds and errors are homoscedastic, then OLS estimators are unbiased, consistent, and best, which means smallest variance among all linear estimators. So, only if three assumptions that we talked about are satisfied, and also assumption about homoscedasticity satisfied, then we can say that we have model which is blue, best linear unbiased estimator. In the case of heteroscedastic model, we need to do the correction, the White's correction, using heteroscedastic robust errors. Okay, if we have a homoscedastic case, good data, we can use, we can calculate t-statistics when the sample is small, and we can use t-distribution instead of normal distribution. So we can use this statistic instead of normal in small samples if all three assumptions hold, if errors are homoscedastic. And regression errors are normally distributed. So it is always like this. But if you don't have homoscedastic case, then this standard error is different because of the heteroscedasticity. In economics, unfortunately, assumptions, conditions 2 and 3 are very rare. So it is very rare that you will run into homoscedastic errors or homoscedastic data. And probably your regression errors won't be normally distributed. So probably you will have to use heteroscedastic errors, and you will look for a bigger sample, which means at least 100 units in your sample, 100 data. This is the end of presentation.